What's up, everybody? Today we're going to be going through Practice Exam 3B. We'll be going through the entire exam, so please feel free to skip around to whatever questions you want to hone in on. Well, without further ado, let's get started. Ooh, a titration curve. How can we analyze this? Well, we see that we're going from an acidic pH to a basic pH, so it must be an acid being titrated with a base. But wait a minute, it looks like a few mini titration curves copied and pasted together. So this must mean we have a polyprotic acid at work. There's a few key landmarks we want to be able to hone in on when analyzing a curve like this. First of all, whenever the pH spikes, if we look to the middle of the spike, we can find an equivalence point. Since this is a polyprotic acid, that means that we're looking at a first equivalence point. And if we look at the second spike in pH, we can see there's a second equivalence point. So that's landmark number one. Landmark number two is going to be if we look at these buffer zones. So for example, the regions where the pH does not change that appreciably. Remember, that's where things are buffered. If we look for the halfway point there, we get our first half equivalence point. And there's another buffer zone up here. That's going to represent our second half equivalence point. And you recall these points are special because at these points, pH equals pKa. And since a polyprotic acid would have multiple pKa values, this is going to be pKa1, and this is going to be where pH equals pKa2. Alright, so let's see what these choices have to say. The acid is a diprotic acid. Well, let's see. There are two equivalence points that we talked about before, which means there are two protons that can be removed. So I like this one. Ding! The acid is a triprotic acid. Now wait a second! We just said it was diprotic. That's malarkey. Point E represents the third equivalence point. Well, you can't have three equivalence points if there's only two protons to take off. So this can't be true. And then 4 is point A represents the first half equivalence point. I like that one. That is indeed true. Ding! So, our answer is going to be C, 1 and 4 only. Okay, the famous scientist Rick T. Cat found himself at the Mount Nittany Medical Center with symptoms including hyperventilation, vomiting, dizziness, and diffuse burning sensation. Uh-oh. Upon examination, it's found that his blood concentration of H2CO3 was 1.5 millimolar per liter, and the concentration of HCO3 minus bicarbonate was 30 millimolar per liter. What's the pH of the blood? Well, how can we go about doing something like this? Wait a minute. Hold the phone here. I think we have an exciting situation going on. For you see, we have a combination of a weak acid, and we have its conjugate base together in the solution. As soon as we see that, we want an alert to go off. Buffer alert, buffer alert, buffer alert, is what it says. So, based off the fact this is a buffer, we can make our lives much easier by using our friend the Henderson-Hasselbalch equation. pH equals pKa plus the log of base over acid. And remember, one of the great things about the Henderson-Hasselbalch equation, it doesn't matter what the units are for the base and the acid as long as they're in like units. It's just the ratio of base to acid there. So, we have a decision to make. Which Ka do we use? Do we use Ka1 or Ka2? Well, since we're relating H2CO3 with HCO3 minus, we need to use the K that relates those two. In this case, Ka1 is the one that relates these particular acid and conjugate base species. So, our pH is going to equal the negative log of Ka1, 4.3 times 10 to the negative 7th, plus the log of base. The base here is the bicarbonate. So I'm going to do 30 divided by 1.5. Okay, so let's see what we end up getting. So we'll end up getting that the pH is equal, it's going to be 6.37 plus 1.30, which ends up equaling a pH of 7.67. Yikes! Someone get a pumpkin spice latte, because that's pretty basic. It looks like Rick T. Cat is suffering from some alkalosis. Thankfully, the good people at the Mount Nittany Medical Center will get him healed. Okay, up next, we're trying to figure out how solubility is changed when we add in NaCO3. So sodium carbonate, it's worth remembering that all group 1 metal salts are completely soluble, which means sodium carbonate is really just a source of well, both sodium plus and carbonate, CO3 2-. So what we have here, since we're looking at barium carbonate dissociating, anytime you add in a common ion, what does that do? Well, it shifts the equilibrium to the left. What that means is by adding in a common ion like carbonate, you're making this less soluble. So choice A is going to be the right one here, because we can see the solubility is decreasing with the more carbonate that we add in. So here we want to balance this reaction under acidic conditions. The first step is going to be to figure out what's reduced and what's oxidized. So in hydrogen peroxide, remember hydrogen peroxide is an interesting case because whenever we do our balancing, we always want to make sure that we account for the group 1 elements first. Each hydrogen in a molecule is going to be plus 1, and since there's 2 of them, that means it's a total of plus 2. So that means that our oxygen then must be at a total oxidation state of minus 2, which means each oxygen is minus 1. Well, now let's try figuring out what the oxidation states on the other side are. Over on the products, oxygen is in its neutral diatomic state, so it has an oxidation state of 0. Meanwhile, in H2O, if we use the same rules that we used before, we can see each hydrogen is plus 1 for a total of plus 2, which means that our oxygen is back to good old minus 2. So, what's being reduced here? Well, look for what element goes from a higher number to a lower number, quite literally reduced. And we can see that the reduction half reaction is going to involve H2O2 turning into H2O. Cool. Now let's set up our oxidation half reaction. Well, our H2O2, our oxygen is going from minus 1 to 0. What? Look at this! The same thing that's being reduced is also being oxidized. This is a case of something called autooxidation or a disproportionation reaction. It just means that the same molecule is both reduced and oxidized. Cool. Now, I'm going to take each of these half reactions one half reaction at a time. So I'm going to first balance the reduction reaction, and then we'll work on the oxidation one. So first we want to balance anything that's not oxygen nor hydrogen. Well, check. Now, we want to balance oxygen. So we can see, here we have 2 oxygens. On this side, we only have 1. Fear not. How can we account for that? Well, we can add in waters. So rather than just adding in plus H2O here, since we already have an H2O, I'm just going to make this a 2. Great. But wait a minute. Now hydrogen's all out of whack. Well, we can easily account for that by adding in H+. So we need to have, since we have 4 hydrogens on this side, we're going to put 2 H+ over here to account for the fact that we already have 2 hydrogens. So now there's 4 on both sides. The last thing we want to do after the hydrogens is make sure the electrons are balanced on each side. So there's 2 different ways you can do that. What I'm going to do is I'm going to check the total charge on each side. Since this side has a total charge of positive 2, based off the 2 hydrogens, this side has a total charge of 0, since water is neutral. That means we're going to need 2 electrons on this side to account for that. Great. Now then, let's balance the oxidation half reaction. Since oxygen is already balanced on both sides, now we need to balance the hydrogen. So I'm just going to put plus 2H+. Now then, everything other than oxygen and hydrogen are balanced. Oxygen's balanced, and hydrogen is balanced. So we are ready to move on to electrons. This side has an overall charge of positive 2. This side has an overall charge of 0. So in order to get the 2 sides on an equal playing field, we're going to need 2 electrons over here. Great! Now both of our half reactions are balanced. The last thing that we need to do is to make sure that the electrons are balanced in both the reduction reaction and the oxidation reaction. There needs to be an equal number of electrons involved in the reduction and the oxidation, of course. So, we've got 2 electrons in the reduction, 2 electrons in the oxidation. Well, that worked out nicely. There's no need to change anything. We can just combine and enjoy. First, our electrons should always cancel out on both sides. Great. Next, let's take a look at the hydrogens. Well, there's 2 hydrogens here and 2 hydrogens here, which means that the hydrogens also cancel out. That looks to be everything that would cancel out, so we can write our overall reaction. It's going to be, we've got 2 H2O2s, one from the reduction reaction, one from the oxidation. So 2 H2O2 is going to yield 2 H2Os and O2. And here we have a nice balanced reaction. Woo! To get back to the question at hand, how many electrons were transferred when we balanced it? Well, it ended up being 2. So that is going to be our answer. In this problem, we have a solution that has both propionic acid, that's actually what gives Swiss cheese its interesting pungent flavor, and sodium propionate, which is just a source of the conjugate base. Wait a minute, we have both this and this in a solution. Conjugate weak acid, weak base pair. We have a buffer! Woo! But now we're adding HNO3 to our buffer. So let's figure out what the HNO3 is going to react with, shall we? HNO3, nitric acid, is a strong acid. When we do a titration in this course, does it matter if we use HCl or HBr or HNO3? No, it doesn't. What matters is that we have a source of H+. So I'm just going to cross this part out here because I know that we're adding in H+. Whenever we do a titration, we need to ask ourselves, what is the reaction going to be? H+, is it going to want to react with the acid component that already has a proton, or the basic component that would like to gain a proton? Well, it's going to be the basic component. So using that fact, we can write our overall reaction for this titration. Our overall reaction is going to be C3H5O2 minus, the weak base, plus H plus. Now remember, anytime we add a strong acid or strong base into a solution, it's always going to be a full-headed arrow, because this thing is not messing around. It's going to react all out. And they're going to form the conjugate acid, HC3H5O2. Anytime we do a titration and have a full-headed arrow, when in doubt, we're going to ISF it out. Use an ICF table. Anytime there's a strong acid or strong base added in, ICF is the way to go. Remember, ICF tables use moles. So one of these we're given the moles for. We're given the moles of the H+. So I'm just going to plug in 0.04 right here. But now we need to figure out the moles of our weak acid and conjugate weak base. So let's do just that. So the problem tells us that the 1 liter solution is 0.1 molar in the propionate, the sodium propionate. So if we do this, we're going to end up getting the number of moles of the sodium propionate, which will end up being 0.10 moles. Great. Let's plug that in. We can do the same thing for the propionic acid, except our 1 liter solution is actually 0.3 molar in the propionic acid, which gives us 0.3 moles of that. Now we have everything we need. Choose the limiting reagent. That's going to be our change. Minus 0.04, minus 0.04, and on the other side it's going to be plus 0.04, which will give us 0.06. It's a terrible looking 0, but you know what? We're going to deal with that. 0 and 0.34. Wait a minute! After we did our titration, we're left with both the weak acid and its conjugate weak base. Again, I don't mean to alarm you, but you know what we've got? It's a buffer. Neat. Considering we have a buffer, we can use Henderson-Hasselbalch now. pH is going to equal pKa, the negative log of the K value, 1.3 times 10 to the negative fifth, plus the log of our base, so this is our base component, 0.06, divided by our acid, which is 0.34. This will give us that the pH is equal to 4.89 plus the log of this ends up being negative 0.75. So that means that our pH, when this is all said and done, is going to end up being 4.14. Okay. So for this problem, we're comparing which one of these 3 sparingly soluble salts has the greatest molar solubility. Now, the thing with this is, if they were all like salts, what I mean is if they all broke in the same number of ions, we could just compare the KSP values, because the math would end up working out algebraically the same way. The thing with this is we have 3 different types of salts. What I mean by that is this breaks into 3 ions, this breaks into 2 ions, and this breaks into 3 ions. So the math ends up changing when we calculate the molar solubility of each of these, which means we can't just look at the KSP values. Just as a spoiler alert, since this one and this one break into the same number of ions, we can look at the KSPs and say, well, 3 must be more soluble based off of the fact that it has a larger KSP. But let's go through and do the math for all of these to make sure that we get the right answer. For molar solubility, when in doubt, I really hope you yelled ice it out. We're going to do an ICE table to figure out the molar solubility. With a solid, we don't care about the initial amount. And unless told otherwise, we've got 0 of this and 0 of this. The change is going to be minus x plus x. And since we get 2 of these for every 1 of these, plus 2x. We don't care. Minus x is still we don't care. 0 plus x is x, and 0 plus 2x is 2x. Great. Now we have our ICE table done, and we need to pair it with our equilibrium expression. KSP is going to equal products, so iron 2 plus times hydroxide squared. Always write out the equilibrium expression. Really easy to overlook something if you don't. So, let's plug in our values and solve and see what we get. Our KSP for iron hydroxide is 7.9 times 10 to the negative 16th. And that's going to be equal to, let's see, iron is x, hydroxide is 2x, and we need to square that. So this is going to end up, when it's all said and done, remember we need to square the 2 and the x, so that becomes 4x squared times x, which means this equals 4x cubed. Once we do the math, we'll end up getting that x is equal to 5.8 times 10 to the negative 6th. And remember, x represents our molar solubility here. So, 1 down, 2 to go. Up next, we're going to be solving for the molar solubility of barium sulfate using our KSP value found here. So remember, a KSP means that we're breaking apart a solid salt. So we'll take barium sulfate, solid. It'll dissociate into barium 2 plus, which is aqueous, and the sulfate anion, SO4 2 minus, also aqueous. We'll write our ICE. We don't care about the solid. This is 0, this is 0. Minus x plus x plus x. We don't care, minus x is we don't care. 0 plus x is x, and 0 plus x is x. Okay, so now we have our ICE table. It's time for us to move on to our equilibrium expression. KSP is going to equal the concentration of barium 2 plus times sulfate. So we'll plug in our values for this. The KSP is 1.1 times 10 to the negative 10th. And then x times x, as we got from our ICE table, is going to end up being x squared. So see how the math is different for this salt here. That's why it was important to do our ICE table. Now then, let's find out what we get. We'll end up getting x is equal to 1.0 times 10 to the negative 5. And that's going to be our molar solubility for this particular salt. So remember, if you have any fears about doing your ICE table, or about solubility rather, do your ICE table, and that will help barium. Finally, we're going to solve for the molar solubility of silver carbonate. Now, because silver carbonate breaks apart into a total of 3 ions, it turns out that the math to the ICE table works out very similarly to how the iron hydroxide did. So I'm going to skip to the step where we plug everything into our equilibrium expression here. So KSP is going to equal 4x cubed when it's all said and done. Plugging in our values, 8.1 times 10 to the negative 12th is equal to 4x cubed. Now let's solve for x and see what the molar solubility is. So x ends up being 1.3 times 10 to the negative 4th. Okay? So it works out that silver carbonate is actually the most soluble of these 3 sparingly soluble salts. And we wouldn't have gotten that if we ignored our ice tables, because this K value is actually smaller than this K value. So icing for the win! So the order of these is, this is the least soluble right here. So 1 is the least, followed by 2, followed by 3. Great.